Hello everyone. In this video and a few more videos, I'm going to talk about representing the orientation of the object or the rotation of the object from one frame to another or from one orientation to another. So there are several ways in the literature that we describe the rotation of a rigid body or the orientation of the rigid body with respect to a frame. One of the most common one that we use a lot in engineering and robotics application is called the rotation matrix. Some people will also call it a direction. If you ever hear this word, they also call it a direction cosine matrix or DCM. Okay, so just in case you ever heard this word DCM or direction cosine matrix, that's another word people use to describe the rotation matrix, okay, DCMs. So now what is it? So let's say here I have two frames, frame 0 and frame 1 with their axes x, y, and z. And let's say your rigid body rotates from one frame to another. So let's say initially the orientation of it is determined by frame x naught, y naught, z naught. Let's say this frame x naught, y naught, z naught is, or in general x, y, z here is attached to the rigid body. Okay, so the orientation of it can be shown like that. And now it rotates such that the axes of XYZ attached to the rigid body, you can call them X1, Y1, and Z1. And these guys with knots can now represent the original frame, or they can represent like an inertial frame with respect to which you are measuring the orientation or the rotation of the part. Okay, so here, one way to describe the orientation of this frame 1 with respect to 0, as I said, is using a matrix we call rotation matrix, and we show it with R10. Okay, so this notation of R10 means rotation or orientation of frame 1 with respect to what? Frame 0. So in general, it has a format like this, that the bottom is the new frame, and the top one is what? The old or reference frame. Okay, so this is the notation that we are going to use from now on. Rotation of the new frame with respect to what? Old or reference frame. And the way you describe it is, this is a 3x3 rotation matrix. And if you look at it, it has 3 columns. Okay, column 1, column 2, and column 3. What is column 1? If you look in the column 1, it is basically the unit vector along x1 axis. So this unit vector described in terms of what? X naught, y naught, and z naught. So you describe this green vector in terms of these 3 blue vectors, these unit vectors that are along the original system. So if I ask you what is the green vector in terms of the blue vector, then you say, well, what I can do is I'm going to project it along these 3 axes, right? So I'm going to project it like this, and then I project it here on the, let's say, x naught, y naught plane, and then project this on the y naught, project it on the x naught, and also perpendicular, I would project it on the z naught. Okay, and then this guy here, this one and this one are going to be the components of that x1, right? So, and that's how you do it in physics or any other course, right? So if I ask you to decompose this x1 along the x naught, y naught, and z naught. That's how you do it. So here, these guys represent unit vectors. And if you want, you can also show all of them with what? With the hat. Right? You know, when you use hat, it means the unit vector. So here, these guys are all unit vectors. And what does dot do? You might say, well, what's the rule of dot? What's the use of dot? Well, you know, based on what you learned, hopefully, in the past for dots, you know, a dot represents what? You're right. The dot represents projection. That's what the dot operator does. It projects one vector along the other one, or it does give you the cosine of the angle. Angle, of course, what? Between the two vectors. You know, for example, here, if I calculate this first component here, this entry 1, 1, when we say x1 dot x naught, what is that? It's the magnitude of the first one, which is 1, that's a unit vector, times magnitude of the second one, which is another 1. That's another unit vector, times cosine of angle between them. If you call that angle theta, it's going to be 1 times 1 times cosine of theta. So you see clearly it gives you the cosine of angle between what? x1 and x naught, which is like this angle here. If you call this angle theta, that is the cosine of this angle. Or the second one is the cosine of angle between x1 and y naught, which is like cosine of this angle. Right? So for example, if you call this angle phi, then you see that the next one here, x1 dot y naught, is going to be cosine of phi, and then for example, x1 dot z naught is going to be cosine of psi, where psi is, let's say, this angle here. Okay, so you see the first column of your R vector is going to be like cosine of theta, cosine of phi, and cosine of psi, correct? And the same thing applies for the other columns. If you look, the next column is all of those angles, but for unit vector y1. So this time, instead of focusing on x1, you are going to focus on y1, which is this guy here. You project that along the 3 unit vectors, and then next time you project this one, this one, which is z1, you project that along the 3 original unit vectors, correct? So what you will have is actually is going to be cosine. All of them are cosines, and they are cosine of 9 different angles, right? That's why we call it direction cosine, because each one of them is the direction or the cosines for the direction of one of these vectors, x1 or y1 or z1. So again, if I want to summarize it, each column of that is the projection of one of the new unit vectors along what? All of the old unit vectors. So that is all for x1, this is all for y1, and this is all for what? z1. Okay, so by these 9 cosine values, I'm going to determine the orientation of unit vectors of frame 1 with respect to frame 0, and this way I can completely describe the orientation of frame 1 with respect to frame 0. Okay, so that's the nice thing about this direction cosine matrix, or the rotation matrix, which is very clear once you have it. Making the orientation clear is not the hardest thing in the world. Okay, it's very easy to understand. Good. Now let's talk about a few other things. One is this rotation matrices are redundant. Why? What's the meaning of that? Well, you know that in general in space, a rigid body has 3 degrees of freedom for rotation. It can rotate in 3 independent ways, right? That's it. So ideally, you only need 3 parameters to define the 3 rotations that the rigid body can have, right? if you only use three parameters, three variables to describe the rotation of the rigid body in the space, that's not redundant. But in a rotation matrix, you know how many entries do you have? 9 of them. You have 9 entries, and 9 entries means 6 of them are what? Really redundant. But it doesn't mean that I can throw 6 of them away. No, but these redundancies mean that I have constraints. I have constraints among these elements, okay? So what are the constraints? Well, if you look at any of these columns, you'll see that the magnitude of each column is what? For example, let's look at the first column. What is the magnitude in the first column? So if I call this whole first column, let's say R1, correct? Vector R1. This guy, I call it vector R2, and this guy I will call vector R3. So what relation exists between R1, R2, and R3, and also what about their magnitudes? So first thing first, what is magnitude of R1? What's the magnitude of this? You know, it's the square root of the first component square, second component square, third component square, all added together. And you know the first component is cosine of theta, so this is going to be like cosine squared of theta, plus the next one is like cosine squared of phi, and the next one is like cosine squared of psi. And you know, for any vector in the space, sum of these squares of these cosine squares is 1. So you will get square root of 1. And since this is magnitude, the answer is going to be 1. So that's right. Each one of these columns, and the same for R2 and the same for R3, okay? So this is equal to magnitude R2. And this is also equal to magnitude R3. Now for them, the angles are different, but the result is the same. Their magnitudes of all columns is equal to what? Equal to 1, okay? So that's 3 constraints right over there. Magnitude of the first column is 1, magnitude second column is 1, magnitude third column is 1, okay? So for example, as I said, if you show your rotation matrix here with 9 numbers, let's say you show your rotation matrix with 9 numbers, R11, R12, R13, R21, R22, and R23. Similarly, 31, 32, and 33, right? There are 9 numbers to describe the rotations. And you know, you only really need what? 3 of them, but as I said, you have constraints between these numbers. And what are they? The first one is magnitude of the first column is 1. So we can say that R11 squared plus R12 squared plus R13 squared is equal to what? 1 squared, or 1. The same thing applies for the second column. I guess I have to change these guys. This is going to be 2, 1. This is going to be 3, 1. And this is going to be 3, 2 squared. And this is going to be 1, 2. And similarly, R13 squared plus R23 squared plus R33 squared is also 1. So you see here, I have 3 constraints already between these 9 numbers. But that's not only it. If you look at the relation between these columns, you can see that each column is perpendicular to the other one. Why? Because all you have in the first column is actually what? Vector x1 written in frame 0. The second column is vector y1 written in frame 0. And what relation exists between vector x1 and vector y1? You know, x1 and y1 are always what? Perpendicular to each other. The set of frame here we are using is a set of perpendicular frames and right-handed. Okay, so each two of them are mutually perpendicular to each other, and they are a right-handed system. So x1 and y1 are perpendicular to each other regardless of you are writing them in what frame. The same for x1 and z1, and the same for y1 and z1. Okay, so the dot product between the first column and the second column is 0 because the first and second column are what? Perpendicular to each other. All you need is here to dot product the first element by the second one, add it to the next, and add it to the next, and you'll see that the result is going to be 0. Okay, so the first column and the second column are perpendicular, which means what? R11 times R12 plus R21 times R22 plus R31 times R32 is equal to 0, because the first and second column are perpendicular. You can do a similar thing here. This is R13 and then R21 times R23 and then plus R31 times R33 is equal to 0. And then the second column is perpendicular to the third one. Okay, so these are my 6 constraints. I have 9 numbers, but there are 6 constraints, and that's what makes 6 redundancies. But these constraints are not so simple that they make me, I threw one of these parameters away and choose another one. And specifically from the first 3, yes, I can, for example, eliminate the last row and replace it by some square root of the first 2. But I would rather keep them like this and not incorporate my constraint into my rotation matrix. Okay, so that's the meaning of constraint and redundancy. The other important thing is, the good and bad thing about it is the calculations. Okay. Now, for here, before that, let's talk about the orthonormal matrices, and then we come back and talk about this loss of accuracy. So when a matrix has all columns of unit vectors, right, because of the matrix has all columns with magnitude 1, we call the matrix normality. Okay, means the magnitude of each column is 1. And because each column is perpendicular to the other one, we call it orthogonal. So if a matrix has columns perpendicular to each other, we call it an orthogonal matrix. If it has magnitude 1 in all columns, we call it normal. So this one has both of them, therefore we call it orthonormal. Okay, so orthonormal means orthogonal and normal magnitude of 1. So rotation matrices are orthonormal matrices, and the meaning of that is clear as we shown. And the orthonormal matrices have some very interesting properties. One of them is that if you get the determinant of these matrices, and I'll show you, the determinant is positive or negative 1. When is positive, when is negative? Positive is if the system is right-handed. Negative is if the system is left-handed. So here that we chose a right-handed system, then the determinant of these matrices is going to be positive 1, and I'll show you. The other one, which is the most important property of them, is that if you want to invert the matrix, all you need is to just transpose the matrix. That's the most important property of these matrices. Because, you know, in general, inverse of matrices is a costly operation. Now, not necessarily for a 3x3, but in general, it is quite more demanding, right? You have to form the R star and divide it by determinant of R to get R inverse, while transpose is just shuffling the rows and columns, which is way easier. And especially when we go and try to do analytic formulas or parametric stuff, this transposing is way simpler than inverting something. So instead of inverting, you can simply transpose them. And again, that's also not really hard to show. I can show you that if you want, but for that, I refer you to my videos that I'm going to make on linear algebra. I'll talk about this and prove it, but not here. And the other thing is, for example, we have to talk about this a little bit separately, but if you want to find, for example, the rotation matrix that is frame 0 with respect to 1, because here what we had is frame 1 with respect to 0, if you look. But if you want to do the opposite, you want to determine the orientation of frame 0 with respect to 1, what you really need is to take the rotation matrix that we had, which was frame 1 with respect to 0, and take the inverse of it. Okay, so this one takes you from 0 to 1, this one takes you from 1 to 0, and these two operations, you can show that they are like inverse functions. They are like inverse of each other. So this one is inverse of the other, but since the inverse is the same as transpose, instead of inverting it, I'm going to transpose it. And you're going to see this is very useful later when I come and solve problems for you. Okay? So that's some of the very important properties of it, but that's not only thing. Actually, the matrices that are 3 by 3 matrices and they are orthonormal, in linear algebra, we say that these guys are forming a group. Okay, they are forming a vector base, a group, and not a vector base, a group, sorry, a matrix group. And we call them SO3, special matrices of dimension 3. And what's special about it? You can show that. So the R matrix belongs to, it's a rotation matrix, belongs to category SO3. And what's so special about this? What's the meaning of that? Well, you can show that if I have a rotation matrix of R1 and I have another rotation matrix of R2, or maybe you call it A and B, whatever you want to call them. Let me just call them R1 and R2. So if you have two R1 and R2, they both belong to what? They both belong to these rotation matrices. Then you can show that if you multiply them together, the product also belongs to the SO3. So the product of any two rotation matrices is also a rotation matrix. Okay, that is very important. Why? I'll show you. When we do rotations one after each other, so we compose rotations together, right? We have subsequent rotations. The way that we can replace all of those subsequent rotation matrices with one single rotation matrix, we call it an equivalent rotation matrix, is to simply multiply them together. And now the question is whether when we multiply all of these matrices together and find an equivalent rotation, is that a rotation matrix? And the answer is yes. Okay, so this is one of the very important properties of the rotation matrices. And I can also write that for you somewhere because it is extremely important. Okay, so rotation matrices belong to SO3, and the product of two rotation matrices is another rotation matrix. Okay, this is very important property which allows us to multiply them together, get an equivalent, and still keep it as a new rotation matrix. Okay, this is very important. Good. So now with that in mind, What's this problem I mentioned, the loss of accuracy in arithmetic? What's the meaning of that? So they are redundant, they are easy to understand and visualize, but what is this one? Well, this one means that I told you that when I multiply two rotation matrices, I should get back another rotation matrix. And what does it mean that I should get another rotation matrix? It means that, for example, if I calculate the determinant of that should be what? 1, right? Or the inverse of it should be the same as the transpose of it, correct? Now, is that the case? And you are going to see that the first or second time or so you try to do it, you are not losing a lot of accuracy. But if you keep multiplying these rotation matrices over and over, because of the round of error, you're going to, after a while, end up with matrices that are not really a rotation matrix anymore. What does it mean? It means now if you calculate the determinant, you see that determinant is not 1 anymore, and their inverse is not the same as transpose. Now, to give you an idea, I know I have to go into the formulas deep and show you, but it's a good idea if I just show you a demo of it very fast right now. And what do I mean? So one of the rotation matrices that you will see later, and I'm going to basically prove it to you, is a rotation matrix like this. This is when you rotate about the z-axis, or here, this one is actually, the first one is x-axis. If you rotate about the x-axis, this one is the axis. Doesn't matter, you can use one of them. The rotation of about the x-axis with angle theta, the rotation matrix forms has a form like this, right? So here, and theta could be any angle. So I'm going to plug in a number for theta, and I'm going to get a rotation matrix about the x-axis. And maybe I get another one for y-axis or z-axis, and then I keep multiplying them together a bunch of times. And each time I'm going to check whether the resulting matrix has a determinant of 1 or inverse equal to transpose, right? So for that, I'm going to MATLAB, and I define a rotation matrix R1, and I say, as you can see here, I'm going to use this guy here, okay? So it is going to be 1, 0, and 0, and then 0, and then cosine of theta, let's say theta is pi over, let's say 6, and then negative of sine theta, let's use, you have to use the same angle, and then 0, and this is going to be sine theta, and this is going to be cosine theta. And you know, in MATLAB, you have to use, when you say sine and cosine, you have to use radians. If you want degrees, you have to say sine d and cosine d, okay? So this is your X matrix, correct? And now, if I say what is the determinant of this R1, you clearly see it is 1. And if I say what is inverse of R1, you see the result is the same as if I say R1 transpose. Right? You see they are exactly the same thing. Now, of course, here, if there are round off errors, you cannot see that well. And the reason is you're only seeing 4 decimals. So one thing I do, I increase the number of decimals in MATLAB so that you can see the changes better. And I'll show you that. And then we have to talk about one other disadvantage. But for now, let's say here, I multiply R1 by itself. And as I said, let me increase the decimal. So I say format long. Okay, and now I multiply R1 by itself, and maybe I call it R2. So R2 is equal to R1 times R1. And let me do it a bunch of times. So, or let me even raise it to a power. You know, when you raise it to the power 10, that means you are multiplying it 10 times what? To itself, correct? So that's like 10 times product of matrix R1. So here I did it, and now you can see the numbers, correct? Now if I say what is determinant of this R2, you see, still not too bad, right? 10 times still keeping it, And if I say what is the inverse of R2 and what is the R2 transpose, if you look, the numbers are almost exactly the same, right? There is no difference as far as I can see. So it's not really too bad, and one of the main reasons here is I'm multiplying the matrix by itself. If comes another matrix which has a different form, like maybe I bring one of these y's or z's and multiply, and if I do it a little bit more than like 5, 6, 10 times, like 100 times or something, now I see the accuracy is dropping. Okay, so here, let me do something. Let me say I create this, let me clean up this matrix R2 and use it for another thing. So let's say this R1 was the X rotation. Now I define a Y rotation. I call it R2, or maybe let's call it just RY. Why should we call it R2? So this is a form of cosine of the angle, and for this one let me use a different angle, pi over maybe 4, and then you have 0, and then you have sine, and then you have 0 and 1 and 0, and then you have negative sine and 0 and cosine. Okay, so this is the Y rotation matrix, and I would call R1 also Rx, if you don't mind, and clean up R1 because it's better to give them meaningful names. So I have an Rx matrix, which is an X rotation, and I also have a Y rotation. If I want, I can also create a Z rotation matrix. And here, for this one, let me use pi over 3, and the Z rotation is going to be cosine, right? You know, the Z rotation has 0, 0, 1, 0, 0. So you are going to get cosine, negative sine, sine, and cosine, as you can see here. Okay, so the cosine is there, fine. The next one is negative sine. Then you get a 0. Then you get a sine. Then you get a cosine. Then you get a 0, and then 0, 0, 1. Okay, so it should look like this. Good. So I define all of my 3 basic matrices, and now I multiply them together. So let's say R equals this Rx to the power 4, then times the Ry to the power 5, and then times, let's say, Rz to the power 6, something like that, whatever, 3, 2. Okay, so I carry out all of these, and I'll get this rotation matrix R, right? Which is the result of 4 times rotation about X, followed by 5 times rotation about Y, followed by 3 times rotation about Z, current Z. We'll talk about that. And now I say, what is the determinant of this matrix? And you see, still it is showing me 1, and then that's not too bad, right? It's relatively good, actually. And now let's invert it and then transpose it. And if you look at the numbers, still not a bad idea, right? Still not too bad because all of the numbers are the same. Now, if I go and raise these powers a little bit and calculate the determinant again, now I start to see the errors coming up. So when we say they lose accuracy, it doesn't mean that if you multiply them a few times, 5, 10 times or so, you are going to get errors. No, this is for lots of errors. And you might say, well, where would you do all of these errors? Well, I'll tell you, when you do lots of rotations after each other, right? So you want to calculate the current orientation of the coordinate frame, and you came over lots of small rotations from the initial to the final, right? So let's say your system has a controller. You want to go from orientation 1 to orientation 2. And each time you have incremented the rotation, right, through a loop, through a numerical solution, and changing your angles bit by bit to ultimately get to your final thing. So let's say if this control loop has a sample time of, let's say what, 10 milliseconds, and your total time it took you to go from position 1 to position 2 is like 2 seconds, right? So 2 seconds sample point of 0.01, it means what? 200 samples, which means 200 different rotation matrices each time that were calculated. Each time was multiplied by the previous one to get you the current orientation. So yes, in 2 seconds with that sample time of 10 milliseconds, if you're each time calculating a rotation matrix and multiplying to get your current orientation, you have already multiplied 200 of these R's together. So something like this with like here 120 times multiplication, that's not really something so out of ordinary. Yes, in the problems we solve in the class, yes, maybe at most I use 1 or 2 times rotation of this or that. But in real life, when you're controlling the rotation of a robot or something, your controller is calculating these R's, multiplying them together a lot. And the problem, you see that now, still not a big deal, it's after so many decimals. But if this thing is continued, and now you might get like 100 here, and maybe 150 here, and maybe 130 there, right? And now calculate the determinant. Now you see that the error is getting bigger. And so if this process is continued and once in a while you don't reset and calibrate your system, not calibrate, but reset and home it and make sure that exactly you can go back to 0 and restart calculating R's, this error starts accumulating, and now these non-zero numbers are getting closer and closer to your major decimals, and once they get somewhere here or so, now you do not really have much of a good rotation matrix, okay? Or if they come to this first decimal, right? If it's instead of 1, it's 1.2 or 1.3, now you have some big accumulated error. Okay, so clearly it takes some time, some multiplications, a bunch of them, but you will start getting accumulated error. And this is faster than one other method that I'll talk later about it, and that is called the unit quaternions. Okay, that's one thing. The other thing is when you multiply two matrices 3 by 3, how many operations are you doing, right? That's another important thing is when I multiply a 3 by 3 matrix by another 3 by 3 matrix, correct? So here I have 9 numbers, and here I have 9 numbers. And then here I get again 9 numbers. The question is, when I want to get this first one, right, how many operations am I doing? So we want to calculate the computational demand of multiplying two rotation matrices. How computationally demanding is this? Well, in order to get that first element, I have to dot product the first row with the first column. So here I'm doing a multiplication of first one with first one, multiplication of second one, third one, and then what? I add these 3 numbers together. So first add the first one to the second one, the result of that to the third one. So to get this, I need 3 products or 3 multiplications and 2 additions. Correct? So that's the amount of calculation for one element, 5 operations. And now you have 9 of them, so it gives you what? 45 operations. So in order to multiply 2 rotation matrices, I need 45 basic arithmetic operations to make it happen. And that's not as many in the other methods of representing rotation, including Euler angles, axis angle representation, and the unit quaternion. Their computations are quite smaller. They need way fewer operations than the rotation matrix does. Okay, so they have redundancy. They suffer from arithmetic accuracy loss due to round-off errors, and the product of them is computationally costly. Okay, because you have to do lots of basic operations to make it happen. But the good thing about them, as you saw, is they are quite easy to understand. They are easy to visualize. Okay, so hopefully I could make my point understood about the pros and cons of a rotation matrix. Now, with all that being said, let's look at one example together first, and then we go look at the basic rotation matrices and so on and so forth, right? So these guys we will call basic rotation matrices, and we are going to derive them, and I'm going to show you how to work with them. So that's my next topic. But before that, I want to look at an example with you. And here I have given you the two frames, frame 0 and 1, and with all the axes shown. So here y0 and z1 are on the top of each other, and the angles between x1, y1, x0, and z0 are given with a 45-degree angle. And the question says, what is the rotation matrix of frame 1 with respect to frame 0? Which, as you know, the first column of that is describing this unit vector x1 along what? Along x0, y0, and z0. Okay, what is that? If I want to decompose x1 along these three axes, how many, what value goes to each one of those? So the first one is x1 projected on x0. Well, clearly, if the magnitude is 1, because we are projecting unit vectors, clearly a vector with magnitude 1 along this direction, once you project it along x0, clearly it is going to be what? Cosine of 45 degrees. What about y0? Well, y0 and z1, they are both perpendicular. So the way they are shown, it means they are perpendicular. These two are perpendicular out of the board toward you. So x1 has nothing along y0 because they are perpendicular to each other. So we can write cosine of 90 if you want, or I would just write 0. Along z0, clearly this sine of 45 degree. Correct? So this is the projection of x1 along x0, y0, and z0. That's your first column. Next, I'm going to go about y1. So what's the projection of y1 on x0? We know that if, since x1 and y1 are perpendicular, if this angle is 45, this angle is also 45. So the projection of y1 along x0 is clearly, again, cosine of 45. It has nothing on y0 because y0 is out of the plane. And for z0, it is sine of 45, but it is in the opposite direction, right? Because when you project this, the z component is the opposite of the positive direction of z0. So this is going to be negative sine 45 degrees. And finally, we go down to the last one, which is z1. And z1 is perpendicular to both x0 and z0. So both of these guys are 0, and it is fully along y0. So this guy is going to be 1. And that's it. This is my rotation matrix. Okay, and as you clearly can see, the magnitude of each column is 1, and each column when you dot product it with the other column, the result is 0. So this is actually an orthonormal matrix, and if you know how to calculate the determinant of a 3 by 3 matrix here, if I just calculate the determinant of R0, 1, you know, if you use the Sarus's law, that is 0, this is 0, you are going to get sine 45 cosine 45 times 1. And then you're going to get, let me make sure, that's 0, 0, 1, good. And then guess I'm making, oh yeah, no, that's right. This is going to be plus minus minus, so it is going to be plus, or I can write it as minus minus cosine 45 times negative sine 45 times 1. And clearly, you know, this guy is, these two negatives would cancel. This is, as you know, 1/2, because this sine of 45 is 1 over square root 2, so times 1 over square root 2. And this is going to be plus 1 over square root 2 again times 1 over square root 2. This is 1/2 and 1/2, you are going to get 1. And if you invert this also, I can easily show you the invert of it is the transpose of it. Let me do it just for the sake of practice, because we said a bunch of things and we need to practice on them. So I say the R matrix is equal to, and this one was cosine, and here I want angles in degrees, so I would go with cosine D. So I have cosine D of 45, and then another cosine D of 45, and then 0, and then I have 0, 0, 1, and then I have sine negative sine 0. Sine negative sine and 0. Okay, so that's my matrix. As I said, the determinant of R is definitely 1, and if I calculate the inverse of R, you see that's the same as what? Transpose of R. You clearly can compare them, and you see that I really do not need to invert it to get what I want. I can just transpose it. And what's the meaning of inverting? As I said, here, if I invert this, right? The invert, which is the same as the transpose, what does that mean? Remember, this shows the rotation or the angles of frame 1 with respect to 0. The inverse of that shows the rotations or angles of what? Frame 0 with respect to 1. So if somebody here says, what is the or rotation matrix of frame 0 with respect to 1? If you have already 1 with respect to 0, don't go ahead and do all these dot products again, or those cosine of the angles. Simply invert or transpose it. Okay, and that makes your life a lot easier once you know one way. The other way is just the inverse or the transpose of what you did. Okay, so this is one example that I wanted to tell you how to work with the rotation matrix, how to find it, and show some of the stuff that we learned. Now, the basic rotation matrices are quite important. Okay, so if you rotate about the x-axis or the y-axis or the z-axis, these rotation matrices, the resulting rotation matrices, are very important. So here, if I rotate my frame that was originally frame 1, frame 1 was at the top of frame 0, but now I rotated everything about the x-axis, right, which is x0 and x1, so those are not going to change. x0 and y0 and z0 are not going to change at all. They are my references. So x1 is going to stay the same on the top of x0, but y1 and z1 are going to rotate with angle theta both, and here any angle that we say is measured counterclockwise positive. So any angle here, when we say angle theta, if we want the positive direction, we definitely align that axis, we want it to be counterclockwise. So here you see z naught is gone counterclockwise to get z1, and y naught is gone counterclockwise to get y1. And now if you project x1 along x naught, you see x1 is fully along x naught, so the first component is 1, and since x1 is perpendicular to y naught and z naught, the next two numbers are 0. So you clearly see why the first column is 1, 0, 0, because x1 is on the top of x naught. Now if you project y1 along the three others, y1 is perpendicular to x1, so the first element is 0. Then y1 along y naught, clearly you see the angle between them is theta. So whatever you have in this direction, you multiply by cosine theta to get this direction, and you multiply by sine theta to get into z naught direction. That's what you see here. And similarly now when you go and project z naught has not z1 has nothing along x naught. So the first one is 0. z1 along y naught, clearly you see when you project something here on the z1 direction, if you want to project it, you will get this guy and you will get this one, and this component along y naught is in the opposite direction, and it is sine but negative sign. That's why you see negative sign here. And then along z naught is, of course, cosine of theta, which you can see here. And that's why you see the third column like that. Okay, so by projecting each one of the new unit vectors along the old one, you get the three columns of this rotation x with angle theta matrix. And you can do a similar thing for the y and the z. I leave it up to you to practice it a little bit, but you can easily show that the y and the z matrices have this form. Again, theta in all of them is counterclockwise. And let me tell you something that maybe helps you if you want to remember them. Something that can help you remember them is, you know, x-axis here, because we have x, correct? We have x, y, z, right? X, y, z. So since this is the x, the row and the column of x, which is this one and this one, they do not have anything to do with theta. They are just zeros or ones. Which one is 1? The xx component. That is 1. Everything else on that row for x and column for x is what? 0. And then the remaining the remaining submatrix, the minor of the matrix, is going to be a 2 by 2 matrix for which the determinant is 1. If you look at the determinant of this guy is 1, clearly. It's cosine squared plus sine squared. And in the case of x and z, it has the same form. If you look here, for example, again, right? You see here, this is x, y, z, x, y, z. As you can see here, the zz element is 1 because the rotation is about z. The other column and row for z are 0. The remaining of that, the minor of that, is a 2 by 2 matrix, again with determinant of what? 1. And the form of that and the form of this one are exactly the same thing. Okay? Cosine, negative, sine, sine, cosine. In the case of y, you have the same principle that I told you. The y element is 1, and the rest of the row for y and the row for column for y are 0. And then the remaining of that, again, the determinant is 1, but this time instead of cosine negative sine is cosine positive sine and then negative sine. Okay, so for y, this 2 by 2 minor is like the transpose of those two others. X and z are the same, y is like the transpose of the x and z. Okay, but it's not really hard once you work a couple of times with these guys to keep them in mind, that how you can write down these basic rotation matrices without really too much of difficulty. Okay, so hopefully that will help you remember these rotation matrices a little bit better. And they're very important, and we can combine them, as I'll tell you in a second. But these are some of the fundamental matrices. Now, let's talk about some other applications of this very big, important rotation matrix. So far, we have seen that you can show the orientation of one frame with respect to the other. Fine, but is that it? Can they do anything more interesting to me? Sure. One of the most important, interesting ones is projecting a point or a vector from one frame to the other. Okay, this is more important. So what it says is this. Let me show you. It says that, well, let me clean up this, guys. So here I have these original x, y, z, 0 and 1 both here, and now my goal is this. I have the coordinate of one point P, and I have the coordinate of this point P in frame what? In frame 1. And now I'm curious, if I project it onto the axis of frame 0, what would that be? So the coordinate of this P is simply going from origin to there, right? That's this vector. The vector is the same for both of the frames in terms of where it is in the space, but the way they describe it in terms of their unit vectors is different, right? Because they are oriented differently. So if I have something here, right, and for example, I say, what is x1? Well, it is going to project that vector onto x1 and say, hey, this is this guy here from here to here, that is your x1. Well, if I say, what is, let's say, x0, then you have to project that onto what? Onto the x0. So you project it like this, you continue x0, and then you project it perpendicular to x0, which is like that, and then this is going to be your x0. Not only you see the magnitudes are different, as you can see, the directions are different. Clearly x0 is negative, x1 is positive, right? You clearly can see that. Or if I say, what is y0 and y1, then again, you do something similar. You project it onto the y0 axis and y1 axis. So this guy here is going to be your y1. Then if you project it perpendicular to y0, then this one is going to be your y0. Okay, you see, maybe both of them are positive, but clearly the magnitudes are different. And the same thing for z0, right? You see, for example, z0 here is a big thing. It's like this much. While on z1, it is not going to be too much. So you have to continue this guy, project it perpendicularly and perpendicular to that, and then it is going to be like this. It's not too small, but clearly negative. z1 is negative, z0 is positive. So you see the components are different. So how I'm writing the very same vector, the very same coordinate, and this P, or this position vector from O to P, can be any vector. So it's not just a point, it's not just a position vector. This vector OP can be any vector. What do I mean? For example, if I have a vector like omega, an angular velocity, and I want to write this angular velocity vector or a velocity vector or an acceleration vector, I know how to describe that in frame 1. Now I want to know how to describe it in frame 0. If I want to go from one frame to another based on their orientation only, then I can just do it with the rotation matrix. Okay? By multiplying that, and I'll show you. But let me first talk a little bit more about this projection, and then we go into math detail of it. First thing first is where in real life you need to do that. Well, I'll tell you, one of the cases is, let's say here, you are in an airplane or you are in a car or you have a robot. Let's talk about robots, right? We are talking about robots. So here, this is my robot going on an incline, correct? This is my mobile robot is going up. It's a differential drive. And it has a yaw sensor, and it is measuring, and not only it is going up, it can also measure, because this is not like a simple 1D surface. Let's say this is a 2D surface. So let me make it a little bit more realistic. So this is my robot. This is my differential drive robot. And it has a yaw sensor which measures this angle here, this angular velocity. Now, you know it is measuring it with respect to what? It is measuring it with respect to the frame that is attached to the robot. We call it body attached, right? So if you have this frame attached to the robot, let's say this is your x-axis, correct? This is your y-axis, and this is your z-axis. So it is measuring it with respect to the z, but which z? The z that is attached to the body of the robot. But that z is different clearly if your inertial frame with respect to which you want to report something looks something like this. Okay, where here you have x naught, y naught, and z naught. So this naught frame is your inertial frame, and then this one frame here is the body attached that is attached to the robot. When you report, your yaw sensor reports this omega, what it does, this is omega of what? This is this omega, whatever it is, written about frame 1. Okay? What you really want, maybe if you want to create, let's say, a map of the environment, right? It is doing some mapping, right? When you do the mapping and you're using that omega, let's say by mapping, this guy has a laser, LiDAR or something, and it is measuring some distances as well as some angles, theta and d, and then you have to combine that with omega to create the map. But the problem is all of these guys are measured with respect to, even theta and d are measured with respect to this body attached frame, and if you want to accumulate them and put them on the top of each other in different positions and orientations of the robot to create a map in the inertial frame, you have to project all of those guys back into your inertial frame, and that's where you have to project this vector back from this frame to this frame. Okay, and the same thing for airplanes too. When the airplane sensors, they measure the roll, pitch, yaw, if they can. Not all of them can do all of it, right? Of course, because they have limitations. Or the gyros, right? The gyros that you have, they do, at least, not the other sensors, but the gyros do. So the gyros are going to give you 3 angular velocities. And these 3 angular velocities are definitely measured with respect to a frame attached to the airplane. But you know, airplane has gone through lots of different rotations, roll, pitch, yaw. And now if it wants to report its angular velocities to the base, or the base is trying to simulate its motion or find out where it is going, they definitely need to project everything along their own inertial system. And that's where you need to do the rotation matrix and use the rotation matrix of the airplane with respect to the inertial frame. Okay, so we use this, and I'll show you over and over that this projection from one frame to another is extremely not only useful, it's extremely needed, and we use it over and over in this course. That's one thing. The other thing is, You might say, well, here, if I look at this frame 0 and frame 1, not only frame 1 is rotated about z, there is also a what? There is also a displacement here. So, you know, a rigid body, not only it rotates, it also what? Translates. So what about that? Well, the matter of fact is, the translation is not going to affect the projection by the rotation only. Okay, so if it's a free vector, and we have to talk about that, if it's a free vector, which means it's not attached to any place, then like this omega, if it's a free vector, if I want to go from this frame to this, all I need is to use the rotation matrix. If it's not a free vector, so it is bound to, let's say, start from the origin, like what? Like this position vector. This guy definitely is bound to start from the origin. It's not free to move. The start point of it is not free. You can move it all around the, you cannot move it all around the space. The start has to be at origin. You cannot replace this vector P with another vector like this, which has the same magnitude, the same direction, but the start point of it is somewhere else. These two are not the same because that's a position vector. But if it was a vector like omega that you made, and that omega is free, that you can pick it up from here to put it another place, then all you really need is the relative rotation of the two. But what about the case of this, that the vectors are not free, when you want to go from one frame to the other, and there is both rotation involved and translation? I'll show you. That's one of our future lectures. And that's where you combine rotation and translation into one matrix, and we call it the homogeneous matrix or homogeneous transformation matrix. Okay, so I'll show you how to combine that displacement D with your rotation R, and actually, speaking of which, this is R, that's not H, and then go from one frame to the other when there is both translation and rotation. So for the moment being, we are assuming that the origin of the two frames are on the top of each other. So the only thing involved here is a pure rotation. Later, we are going to involve translation as well. But for the moment, just keep it with me that we only have single rotation. Now, let's go back to the question I asked. I give you the coordinates of point P as written in frame 1. So I give you P of 1. P of 1 is here what? Coordinates of point P as written on frame 1. So these 3 x1, y1, z1 that I showed you. I also tell you how you went from frame 0 to frame 1. Okay, so I give you this rotation matrix, and then I ask you, okay, now if I decompose P onto frame 0, what is going to be the coordinates x, y, and z? And it's not really hard to show that. All you need is a simple product. And you can easily show that here. Why? Because the coordinate of P in frame 0 is simply what? Vector P, whatever it is, dot producted with x naught, y naught, and z naught, right? You know, whenever you want to write any vector along any axis, all you need is to do the dot product. That's what we did with the columns of the unit vector. And what is P? P can be written as the component of it, U. So here, the component of P along x1, y1, z1, I call them U, V, and W. So it is equal to U times x1 plus V times y1 plus W times z1. This is how I am writing my P along frame 1, right? And dot product is with x naught, y naught, and z naught. If I do that and expand here the dot product, it's going to be U times x1 dot x naught plus V times y1 dot x naught plus z times W times dot x naught, and then the same thing for the other numbers. And now what you can do, you can rewrite this as what? As x1 dot x naught, y1 dot x naught, z1 dot x naught, and the same thing for the others. This whole 3 by 3 matrix times the three numbers u, v, and w. If you multiply this 3 by 3 by this 3 by 1, you see the result is going to be this top one, which is the 3 by 1 vector. You clearly can see the result is that. Okay, and now guess what? This guy is your rotation matrix that here you're decomposing the unit vectors of 1 along 0, so that is R1, 0. And these are what? The coordinates, as I said, of point P in frame 1, so I show it with P1. Right? So if I have P of 1 pre-multiplied or multiplied from the left side by R1, 0, it takes you from frame 1 to what? Frame 0. So I get this very important conclusion. Okay, and that's one of the most, if not the, it's one of the most, I would say the most important uses of the rotation matrix, projecting a vector from one frame to another. So again, if I know coordinates or values of x, y, z of P in frame 1, and if I know how to go from frame 1 to frame 0, I know the rotation matrix, I can always get this guy. And you clearly can see my notations here. The notations is these two are the same thing. If I have P of 1, this guy takes me from 1 to 0. So I have something in 1. This guy is taking me from what? From 1 to 0. Therefore, my final result should be what? In frame 0. And you can see the same thing here. I have something in frame 0. This guy takes me from 0 to 1. So the result is going to be what? In frame 1. Okay, so the notation is very clear how we are writing the coordinate of a point and how we are writing a rotation matrix. Okay, so this is one of the most important things. And here I want to show you a couple of examples to digest this topic a little bit better. Maybe for that, we can come here into this example we did last time and try to look at some nice example here. So this is what I do for this case. I consider a point here, and I'll consider that point, and I'll try to make it simple, okay? I consider my point right here, maybe. Okay, so this is my point P. Now, if I ask you what is the coordinate of point P in frame 1, what would you say? So you have to decompose this position vector along x1, y1, and z1. Clearly, and let's say this guy here, you have to decide where this one is. Okay, so here I have not really decided where that one is, how far along x0. Let's say it is 3 units. Okay, so it is 0.3, right, on x0. Okay, but that's not that x0, that's not along frame 1, that's along frame 0. So just this distance is 3 units. Fine. Now, what's the coordinate of point P1 in this frame 1? What are these? Well, I can project them, or I can say that this is equal to, since I can easily find them in frame 0, right? If I say, what is the coordinate of point P in frame 0? That's not really hard, because all it is 3 units along x0. So that's 3, nothing y0, nothing z0. So that's 3, 0, 0. You see how simple is that? Right? In frame 0, because the way it is oriented, the coordinate of P describing in frame 0 is very easy. But what about frame 1? In frame 1, you have to do some projections, and it's not a big deal, but I want to show you how to get it with rotation matrix. So what I say is this. I say this guy, P1, is equal to P0, that I can easily find, times a rotation matrix. Now, what is this rotation matrix? it has to take me from somewhere in 0 to somewhere in 1. So it has to be 0 to what? 1. As I said, it is always R of the new frame to the old or what? Reference frame. That is the notation I'm going to use here. Okay, so it is going to go from 0 to 1 because my goal is to go to 1. So 1 is my reference. If I can find this multiplied by that, pre-multiply, that's it. Now, in this example, I already had 1 with respect to 0, but look here, I want 0 with respect to 1. And remember, I said if you want 0 with respect to 1 and you have 1 with respect to 0, just invert that guy. So if you invert it, inverse of a matrix for rotations does the opposite job. And I said you don't even need to invert it because these are special matrices. All you need is to what? Just transpose it. So all you need is simply transpose that matrix, right? So bring the first row down to the first column. So it makes it 1 over square root 2, 1 over square root 2, and 0. Second row becomes second column, 0, 0, 1, and then third row becomes third column. Okay, so that's the transpose of that matrix, and then multiply that by what? Multiply that by the coordinate of P in frame 0, which is simply 3, 0, and 0. And if you do that, guess what you would get? Just do the multiplication. So it is going to be 3 over square root 2. And then it is again going to be 3 over square root 2. Yes. And 0, right? So this is along x1, 3 over square root 2. Over y1, it is also 3 over square root 2. Along z1, there is nothing. Let's see if that's the case. And you clearly see this vector has nothing along z1 because z1 is perpendicular to that vector. And if I project it along x1 and y1, of course, if this is 2, this is going to be what? This guy here, your y1. This is going to be 3 times cosine or sine of 45. Doesn't matter in the case of 45. And your x1 is going to be what? 3 times cosine of 45. And you know cosine 45 is the square root 1 over square root 2. So you see both components are positive. 3 square root 2. There is nothing along z1, so that is going to be 0, and that is exactly what you got here. Okay, now in this case, it's not so hard to get P1 because you could do this projection easily. And that's not the case when the problem is more complicated like this. So when you have 3 angles involved, none of the axes match any other one. There is no coincidence between the axes of old and new. And you have a point that is not on any of the old or new axes, so something like this. Or forget it, even something like that. If I have even this unit vector, right? And I know P in the frame 0, and I ask you what is P in the frame 1. Well, in frame 0, it's so easy. It's something along the z direction. No x naught, no y naught. But projecting that along x1, y1, z1 needs you to know all of these angles. Okay? And those are indirectly given into what? Their cosine is indirectly given into this rotation matrix. So here, a simple projection, if you don't know the angles, is not that easy, but once I know the rotation matrix, all I do is the product. Okay, so that is one case that I wanted to mention, but here I would like to show you another case, another example of this projection for you here. Okay, the other example that I wanted to mention is involving a little bit more complicated case, and that is about projecting omegas. Okay, if you refer to one of the videos on my channel about dynamics that I published recently, it's a long video, by the way, but I mentioned dynamics, 3D dynamics using Euler angles and gyroscopic effect and so on. That's a very good video. Take a look at it. One of the cases I mentioned is basically describing the angular velocity of the rigid body with respect to the inertial frame, but decomposing that vector onto the frame that is attached to the rigid body. So the physical entity I'm going to decompose, omega. What's the meaning of omega? Omega is the angular velocity of the rigid body with respect to the inertial frame. Okay, that's omega, small omega. But instead of me writing that omega in along the axis of the inertial frame, I want to write that along the axis of the body attached frame. Here, cap x, cap y, and cap z represent the inertial frame that doesn't move, and small x, small y, small z represent what? The body attached frame that rotates with the body, and it has gone through all three Euler angles, psi, theta, and phi, okay? So if you watch that video somewhere around this 1 hour 50 something minutes, you see I'm showing you, and I'm going through all of these pictures one by one, and I'm showing you that if you want to project all of the three angular velocities of the rigid body, the first one is psi dot, which is the object has rotated about the z-axis by angle psi with angular velocity psi dot. Once it's gone to the intermediate position, we call it x prime, y prime, z prime. Now you have a rotation about the x-axis, the intermediate x-axis. And let me see if I have a better picture of it here. Yeah, this is a better picture. So what you have in the Euler angles, and I'm going to create another small video about the Euler angles, just about the orientation problem. But what you have here in this problem was at the beginning, both of the frames are on the top of each other. Again, small xyz is body attached, cap xyz is inertial. First, you rotate about the z-axis by angle psi, and the resulting angular velocity of that, you call it psi dot. So psi dot is about the cap z or the initial z. Then, whenever you get the first intermediate frame, you call it x prime, y prime, z prime. What you do is you rotate now about the x-axis by angle what? Theta. So rotation happens about the x-axis by angle theta, and the resulting angular velocity of that you call theta dot, which you can see here. It is along the intermediate. Then from the second rotation, which is along x, you do a third rotation, this time about the new z, when the angle is phi and the resulting angular velocity is phi dot. So you have three angular velocities, psi dot, theta dot, and phi dot, about the current z-axis, the current x-axis, and another current z-axis. And what you want to do is, if you want to describe the angular velocity of this rigid body with respect to the inertial, right? But decompose that omega, that angular velocity, onto the frames of the current xyz. So whatever it is, Do not decompose it along this capital X, capital Y, and capital Z. Express it in terms of this rotated X, rotated Y, and rotated Z. And how do you go from the cap to the small? Through these three angles, psi, theta, and phi, the three Euler angles, which we call precession, nutation, and spin. And I showed you even how to find the rotation matrix factor, but we are going to discuss it again here. And now my question is, how can I find my omega, right, of the rigid body with respect to the inertial, but describe it into the body attached frame? How can I do that, right? So that's the problem here I'm trying to do, and the answer over there that we did through geometry. So here we did a bunch of projections and geometry, and I showed you that the resulting angular velocity should be like this: theta dot plus cosine phi plus psi dot sine phi psi theta, and then psi dot sine theta cosine phi minus theta dot sine phi, and then phi dot plus psi dot cosine theta. Okay, that's what I have. By the way, here you might see what are the notations that you're using here. So in this course, as much as possible, I'll try not to write sine and cosine, okay, because it takes some time. So from this point on, I will write sine of any angle, let's say alpha, as S subscript alpha, and cosine of alpha, I'm going to write it as C subscript alpha, sub alpha. Okay, so these are some of the other notations I'm going to use: S and C for sine and cosine of an angle. Okay, so this is the result we found through a bunch of geometry and projections, right? And you can refer to that video for the details. Now the question is, can I do it using this rotation matrices? And the answer is absolutely. How? To do that, first I need to come back here and talk about composition of rotations, okay? So here we need to talk about composition of rotations. When you have more than one rotation, how would you combine them into a single rotation, okay? That's the most important thing after their application. Now, how would you combine them into one equivalent? Okay, so let's talk about that, and then we come back and look at this specific example here. Okay, and then at the end we can talk about the similarity transform.